So we'll get started. So in the last period, we talked about Le Chatelier principles, right? So you guys learned that in high school. When you disturb the system, it will want to go back to the equilibrium, which is the minimal energy state, okay? So by looking at this simple reaction here, where you have a gas phase reaction that you produce PCl5 from PCl3 and chlorine gas, okay? So when you see heat of reaction that has the negative sign, what does it mean? Okay, when you see a negative sign, that means it's an ectothermic reaction. So that means it releases heat when this compound forms. The origin of this behavior can trace back to the bonding energy of these compounds, okay? When you do reactions, you will have to break some bond and form some new bonds. When the final energy of this compound is lower than the sum of your starting material, you will release the extra energy to the system. So we recognize heat is a byproduct of such a reaction when it's going forward. What will happen when it's going backward, going from PCl5 to your starting material? That will be exactly reversed, right? You will put a lot of heat into the system and break these extra bonds and form new bonds. So that means when we are in a very hot environment where the surrounding can provide a lot of heat, a lot of thermal energy, this reaction is not so favorable in comparison to lower temperature. So that gives you the correlation between the temperature and the equilibrium constant. The temperature will shift equilibrium constant, so you have to remember that. So since I mentioned a K, and this is just a review, we know K is concentration of your product over a reactant. So when the K is larger than 1, that means product is favored, okay? So if we're looking at this reaction backward, sometimes we will have K1 up here and K minus 1 indicating it's going backward. If the K going forward is less than 1, so if you look at the math for something that's less than 1, that you have more reagent. So that means this reaction will favor going backward. So when we're talking about K, let's look at the other reaction. Okay, the decomposition of N2O4 into 2 of the nitrogen dioxide, okay? This reaction is dependent on the concentration, and there's a picture in the book where the initially colorless vial and it becomes color over time, right? So if we look at the equilibrium constant of such system, if I indicate it by K1 and K minus 1 for it going forward and backward, the equilibrium constant is essentially the ratio of these two rates. And again, we can do product over reactant. The square comes from here. So just to put that into perspective, when you see a K, it could be, you're going to get a different kind of K. And this is just to put it into perspective. When you have such a small number, that means you have a lot of reagent starting material. So that means it favors this side. And when you see a large K, a very big number with a lot of zero, that means it favors product. What does K equal to 5 mean? So that means in the case of these two, these are extreme cases. That means most of the stuff is on either one side or the other. And for K equal to 5, if you put it back to this equation, so that means you can actually observe a decent amount of each two. They are coexist, okay? So the value of K is really dependent on your reaction system. And something you can think about it, the ways you can think about it, you can think about supply and demand in economics. So usually when your supply go up, your price will tend to go down. So there's some similarity between the supply and demand and the rate constant, okay? This is because later on we'll talk about how these reactions is controlled by the thermodynamics, okay? Now we're in kinetics. So now since we talked about the K, I would like to talk about how do we describe the extent of reaction with what we call Q, okay? So Q is another number that would describe your reaction system. The reaction could go either way, and sometimes it will go over, sometimes it's not finished yet, you are at the beginning of your reaction, okay? Because if you look at the product formation, you generally get a curve like this, right? So you're producing product, and eventually the amount is remain constant, and this part is the equilibrium point, okay? But if we're looking at this part, this is a dynamic process, right? There are some product forming, and sometimes it's going backward, right? So how would you describe a system like that? And then this is why we have to use Q. Q is to describe the reaction system at a given time point. You can determine each of these by some advanced spectroscopic technique, okay, analytical technique. You can analyze your reaction system as long as they give you special signature, whether it's absorption, whether it is, if you do a column chromatography and you finally figured out the concentration of each component. So during the reaction, we don't talk about K, we talk about Q, okay? And I know this could be a little bit confusing, and I do not want you to get this too mixed up with K, okay? So when we talk about rate law, there are certain set of rules. But now we're talking about Q, it also has its own set of rules. So if we have a reaction that look like this, so this is kind of similar to rate law, right? But in this calculation, you don't worry about whether this is the right order or not, okay? This is two different concepts. When we're talking about Q, we have a general equation. Again, it's product over reactant. When you learn about more solution kinetics or equilibrium, these exponents will change. There's something called activity exponent, okay? Not all the reactions are perfectly mixed. So when we're talking about these things, we assume it's perfectly mixing, okay? So this will correspond to the rate amount that you put in. But perfect mixing is not a real thing in real world. So if you think about you stirring a reaction very hard, you get a relative homogeneous mixing, but there's going to be some area that's going to have a little bit more of A and a little bit more of B. So the stoichiometry is imbalanced. So therefore, the reaction rate and everything is different. So it's given an equation like this. You should be able to list out the Q calculation, right? And a lot of time, the problem will give you the amount of reagent and then the amount of product. Then you can calculate Q, which describe your reaction system. Then by using Q, we can find out where we are in terms of an equilibrium scale, okay? Did we go over the equilibrium? If your Q is larger than your equilibrium constant, that means you're going over the liquid equilibrium. But if Q equal to K, that means you are at equilibrium. If you do not disturb the system, it will not have further change, okay? So let's look at this reaction backward, okay? Imagine this is your starting material, and this is your product. So let's call that forward reaction and backward reaction. So to describe backward reaction, I mean, in the book, it might say reverse, okay? So there, it's equivalent. So it's exactly product over reagent, right? So okay, so when you see an equation like this, you should be able to recognize, and every reaction, it had both forward and backward directions, and it's just a matter of which position is preferred as dictated by equilibrium constant, dictated by the energetic of your reaction. Is it exothermic? Is it endothermic? Okay? And also has to do with the number. Okay, if you go back to Le Chatelier principle, we're talking about the number of mole of gas, right? It also has to do with the number of molecules present in the system. All right, so there's another thing that is kind of confusing. It generally, when we talk about Q or K, they are unitless. But you can also see some textbook will tell you you will have to cancel out the unit. And then so in reality, either way is fine, okay? But in our book, it says it has to be unitless. Because when we are talking about Q, we always have a reference that we are looking at, okay? So when you have a reference, in the end, the unit will be canceled out, okay? That makes sense? So don't freak out if you don't see a unit when the Q and K is given, okay? They all cancel out in the end, all right? So in some cases, you will see this is either a liquid or a solid, right? So when we are talking about Q, in those cases, the activity coefficient or this coefficient will become 0. So it's kind of like a zero order dependence on your concentration. So when we are talking about Q, if you see something that's liquid or solid, we will simply make that term equal to 1 and cancel out. Okay, so a perfect example would be a reaction between calcium carbonate decomposition into, we put a lot of heat into the system and break these ionic bonds, and you'll get CO2 and calcium oxide. Only this is gas. We know this is solid, this is solid. When we're expressing Q, the CO2 will be the only term when we're talking about Q. That makes sense? So this is just how the Q is being used in this chapter, and I guarantee this won't be used in later chapter, okay? I mean, I know there's a lot of calculations associated with this, but since I want you guys just to get the concept, for this class, you are not required to actually do the calculation on your test, but I think it is a good skill to have. If you have the right concept, know how to do the math correctly, right? It's all about carrying out your calculation in a systematic order and then solve for the X. Then you can get the solution. I think it is good for you to know how to follow calculation steps and not mess it up. Okay, so I keep saying Q, but I should tell you the name of it. The Q, the real name for Q is the reaction quotient. Okay, so if you on the test you see that, okay, then you know, okay, Q, I see Q is asking for Q. Okay, do not get them messed up with equilibrium constant. Q is constantly changing. K doesn't change unless you change temperature. All right, so anybody remember who Van Hoff is? Van Hoff come up with an equation that relate the temperature to equilibrium constant as a function of heat of reaction. Okay, so if you look at page 776, so the simple Van Hoff equation, okay, so you should recognize this is very similar to Arrhenius equation, right? Except Arrhenius equation is delta G over there. I mean, you can treat this as a constant, okay? These are all constant. And you simply plug in the value. If you know the constant value, the heat of reaction, okay, again, when you add catalyst to a system, what happened to the heat of reaction? What happened? If you add a catalyst to the system, what happened to heat of reaction? The catalyst, it will increase both forward and backward rate. And if you remember the plot that I drew over there a couple lectures ago, right? Heat of reaction doesn't change. Okay, you have to remember this, and this is a trick question. Every professor loves to ask this. How does catalyst affect a reaction? It lowers activation energy, but it doesn't change the heat of reaction. How do we get heat of reaction? This would be if we have depending on the scale here, okay? This is called reaction coordinate. If you have heat of formation here, then you get the heat of reaction. If you have Gibbs free energy here, you get the activation energy and you get the delta G of the reaction from this plot. Okay, so now we touch on what happened when you change temperature and how that affects K, right? Now we're going back to practice problem related to this. Hopefully you still remember. Okay, so from reading, we know sodium is a very reactive metal, right? So as potassium and everything in that column. When you put that into water, it reacts violently. And then if you guys read the chapter 16, you would know why, right? It's because it wants to lose an electron so badly so it can get to an optimal electronic configuration, okay? So if we react sodium with water, so, all right, so when I see this, okay, you can either say I memorized the rule, okay? If these are solid and liquid, sorry, I forgot this is aqueous, okay? Solid and liquid, okay, so they are not part of discussion, okay, in the reaction quotient. And you can skip and directly have QC equal to NaOH, and okay, because it produced 2 NaOH, therefore I'll have square and times H2. Alternatively, you can write it all down, okay? Okay, and then recognize, okay, well, in this reaction, we don't care about stuff that is not dispersed, okay? In aqueous solution, NaOH dissociate, right? They're very far apart from each other. They're mostly surrounded by what? Water molecules, okay? That's a very important picture. I'll mention that later on, okay? Then you have hydrogen. Hydrogen is a gas. We know the difference between gas and solid and liquid, right? Their intermolecular distance are very far and they move much faster than the solid and liquid, okay? So recognizing these two are not part of your equation. They're heterogeneous, okay? They're not in the same phase. So these terms equal to 1. So it will still give you the same equation, okay? And another important concept, you have to recognize that sometimes we will have different expression, something we call Q prime, okay? This is just to help you to keep track the mathematical manipulation that you did to your system, okay? So an example here is on page 754, okay? So in the case that you have a imbalanced reaction system, okay? Okay, first we check what phase they are in. They are in gas, okay? So that's great, okay? So if it's not bad for someone with a balanced equation, you will write your Q differently. When you see an equation like this versus an equation like this, the Q, the way you write Q will be very different, right? So if we follow this rule, we will simply put whatever is in front up here, right? So how would I write down this equation? Okay, and in this case, your Q okay. Okay, I know this could be a little bit confusing because I missed a SO3 here. But looking at these two expressions, the way you write down your Q will be different, correct? Okay, so in this case, you will get different value if you plug in a concentration. Okay, so you have to recognize this. If we take out, how can we go from here to here? So essentially, Q prime, if you take a square root of this equation, right? If you take a square root, 2 become 1, and this is 1, you got 1/2 over here. Okay, so that means whatever you calculate out here will be your Q prime. This is now 1, okay? So because the way the mathematical equation is set up, okay? So when someone asks, what is Q prime, okay? Then you have to recognize, how can we get from here to here, or how can we get from here to here? These will be different, okay? So Q prime squared will be equal to the Q that we showed, okay? This is just a simple math, okay? All right, so now let's look at the example 17.2. And now I want you guys to actually walk through the problem. Okay, so most of you know how to do the math, okay? So I will have you guys next week we'll work on a couple problems like this. So the most important part you have to recognize here, for example, if when we're looking at the A, okay? When we see the second equation where you have carbon monoxide react with chlorine, okay, and we immediately should recognize, okay, this is 1 molar of chlorine, but in my final equation, I have 2 molar of chlorine. When I'm describing different equation, right, we will simply times the equilibrium constant together, okay, as long as it's going the same direction, okay. We put the reagent on the same side when we add equation together, but when for their rate constant, we times, okay? Because when you're writing K or writing Q, it's always product over reagent, okay? So when you add multiple equations together, you have more type of product, right? So you just basically throw them on there, and you will get the final answer. If you have different coefficient in front of it, you can simply do something like this. So eventually, you just have an exponent adding onto your Q. And you can do the same thing for the K, okay? Because these are all relative terms. Because in the book, it talks about, you see the small c, right? And small p, right? And the reason why I don't write those is I don't want to confuse you guys. But the C, what C stand for? It's concentration, okay? A lot of time we deal with concentration. Back in the days, it's not so easy to measure concentration, right? So a lot of preliminary experiments were done with pressure. And industrially, when we are carrying out these chemical reactions, a lot of them involve gas, okay? So for chemical engineering, they deal with a lot of this. What's the solubility of gas, okay? Under certain pressure, okay? How can I get most product out of this reaction with minimal amount of energy, okay? This is what they work on. All right, so now we'll talk about pressure, okay? Kp, this is the section 17.3. We all know this equation PV equal to nRT, right? So if we rearrange this equation, so you simply divide RT from both sides and divide V from both sides, and you get this equation, okay? And then so this is something we care about. Again, constant. So when we are talking about a reaction, let's go back to this NO oxidation reaction. If we want to describe this equation for the forward reaction, so make sure you keep these terms so you don't lose track, okay? So it follows the same rules as what you've seen before. But how do we relate concentration to such equation? So this go back to concentration is what? Number per volume, okay? So when we're dealing with gas, okay, we also need to look at the change in terms of number of gas molecules. And for chemists, we like to describe everything in mole, okay? I think Arrhenius come up with that, but I could be wrong, okay? He just used the name word mole to describe number of gas, okay? Okay, so if we look at this change, again, it's final minus initial, okay? It's always finals minus initial, finals over initial, okay? we have 2 mole of gas at the end of reaction, and you begin with 3, so you get the exponent of -1. So in order to relate your QP to QC or your KP to KC, okay, so this is how you will relate. And you can simply derive it if you want, okay? But on your concept exam, this will be given. But you simply, what you need to recognize is, okay, the change. And this is basically, if you look at this equation, you can move this term over here, right? And then this is just how you can relate pressure and concentration. Okay, you can go through the derivation yourself. Now we'll move on and we'll do one more problem, okay, before we move on to the next part of the lecture. So this is your problem, sample problem 17.6. These are the reaction condition I was given. It asks you to calculate Kc at equilibrium, okay? Sometimes you will see time equal to infinity to describe equilibrium, because when you let the reaction run long enough, it reaches equilibrium, okay? From here, we can figure out our initial concentration, okay? Right? And then by looking at the equation, at equilibrium, this is your final amount, okay? So what we can do is, we know it consumed 2 mole of HI and give you one of each of these hydrogen and iodine, correct? Okay, so if we set up the calculation, when we form X mole of hydrogen or iodine, we will consume 2 mole of HI, right? So we can think about setting up the equation. Again, looking at this equation, this, right? Okay? And then we don't know how much. We need to calculate how much is formed, right? So the amount that is consumed, okay, from initially it's 0.1, now it's 0.078. Once it reacts, it will form hydrogen and iodine, right? We know going from here to here, this is at equilibrium, from the initial minus 2x. And then, so we can solve for x, okay? And then we can substitute our x back to this equation. And this is your 0.078 molar, right? And at equilibrium, Q equal to K. Then we can get our K value from such simple mathematic manipulation. There's a lot of example in the section 17.5, and then there are some example that's more complicated. So of course, it's depending on the number of terms that you have in such equation, right? Okay, so sometimes you will have to solve for quadratic equation, okay? So I think that's most of the material for chapter 17. And for the 17, I would like you to focus on the 17.5 has a lot of mathematical calculation and scenario, okay? So if you can work on the problem and then just walk through it, then you can figure out how to do this. But in the end, it goes back to your understanding of how to use these equations, how to express the extended reaction with Q, okay? And we talk about how you can relate concentration, equilibrium constant to the pressure term by using the ideal gas law and taking into account of the number of mole change of your gas, okay? Next, I will briefly touch on the acid and base, and then we'll have a brief chemistry demo. All right, so now I want you guys to get in groups and talk about what kind of properties that acid and base may have, okay? So just name a few properties of acid and base. Okay, so I guess you guys all agree with Arrhenius. The first line, what I see is Arrhenius definitions of acid and base. Okay, so anybody want to tell me the limitation of Arrhenius definition of acid and base? What would be the limitation of Arrhenius definition? Arrhenius is the guy that created Arrhenius equation, right? And during his PhD, he come up with the idea for the acidic compound is dissociate into H plus, or in base will generate OH minus. What is the limitation for such assumption? So for the most important part, such definition is that once the ions are formed, they're solvated by solvent molecules, right? So back we were all talking about water, right? For acidic solution in water, such as lemon juice, it's acidic. If we dissolve some limestone or baking soda in water, like NaH, sodium bicarbonate, the baking soda, into water, it gives us a basic solution. Okay, so the limitation of Arrhenius equation, it doesn't work when you dissolve such as HCl gas into toluene, which is a hydrophobic solvent, okay? So that is a limitation. It says these ions has to be solvated, right? So for a nonpolar compound, it cannot solvate these very well, but you can still do acid catalyzed or base catalyzed reaction in nonpolar organic solvents. Okay, so that's a limitation of Arrhenius equation. And of course, H plus is not a real thing. It is solvated, right? So generally, we will express it as a hydronium ion. Okay, but in reality, one H plus could be surrounded by multiple water molecules, okay? And the water molecule around these H plus are somewhat structured, and that's how you can get very unique property of acid and bases, okay? Another drawback of Arrhenius definition of acid and base is that it failed to explain why amine can function as a base. When you look at amine, if we dissolve, let's look at our favorite molecule, ammonia. Okay. How does it function as base? So we know from common knowledge, when they dissolve in water, it can abstract a hydrogen from water, and then you get the OH minus, okay? How do we get this view? I'm sure your chemistry teacher told you this. This is what happened to ammonia, okay? All right, so then in this case, this is more of what we call the Bronsted-Lowry definition. Okay, so this is the second definition for acid and bases, Bronsted-Lowry. Instead of talking about releasing ions, it talks about donating hydrogen or accepting hydroxide, okay? pH is obviously a very important term to describe acid and base, and then most of you get it. And then why are strong acid corrosive? So when I think of the corrosiveness of acid, I instantaneously think of the reaction between nitric acid and copper, okay? And we'll touch more on this when we talk about batteries. So it had to do with its oxidation power and reduction power, okay? Strong acid generally, they have lots of O. If you were reading chapter 16, it talks about oxo acid, okay? So if we look at this, only one hydrogen is bonded to O, right? So when you have two or more oxygen that is not bounded to hydrogen, it is a strong acid. That's why I want you guys to read chapter 16 on your own, is because I think you guys should recognize how to compare the acidity based on chemical structure, how to predict things, okay? Now we talk about somewhat famous reagent due to this coronavirus. People talk about sensitization, right, with hypochloric acid, okay? This is a very weak acid because by the definition that I mentioned, okay, and there are multiple chemical equilibrium associated with such molecule. And this is why we care about equilibrium, because this describes how things work in real life, okay? And a couple other weak acid, for example, I'm sure you guys see that on your exam, concept, if you remember HCN, it's a weak acid, okay? For example, H2S, they all fulfill, they have no O at all, okay? And HF, if we look at the MO or the electronegativity of such molecule, the bonding is not so ionic, it's more of like a covalent bonding for HF, okay? But this is a terrible chemical that can attack your bone. All right, so another weak acid, vinegar, okay? That's the best example, weak acid. Vinegar, it generates acetic acid. Okay, so how can we tell it's the weak acid or strong acid? So the best way to describe it is Ka, right? So let's define Ka over here, okay? If we dissolve an acid, okay? So when I write an equilibrium constant, but we know this is a liquid, right? And we have a lot, generally when we are dealing with solution, we have a lot of water and very little amount of acid. We deal with dilute solution, okay? When we talk about concentrated solution, it's a total different scenario. We're talking about dilute solution, and it's a liquid that is equal to 1, okay? So then this is what we have for Ka. So Ka, A for acid, okay? It's just product over reactant, nothing special, all right? So when we have a very large K, that means we have a lot of hydronium, right? So that is a strong acid. When we have intermediate K, it is a what? Weak acid, right? So that means a lot of that weak acid did not dissociate into hydronium ion, does not produce hydronium, okay? It only stays at its original state. And then for strong acid, generally they have very large Ka. So strong acid, the best example, so the three most important strong acid: nitric acid, hydrochloric acid, and sulfuric acid. And you should be able to know how to spell them, okay? You should be able to recognize the name in the laboratory, okay? I know one day you guys will go to graduate school. A lot of these labels will be in English, so you have to know what nitric acid is. This is hydrogen chloride, so hydrochloric acid, how we name it, okay? And sulfuric acid, okay? What could be other acid, okay? I talk about HCl, okay, another common one is HBr and HI. These are, so if you read chapter 16, it talks about acidity of these things, right? So you should know why HF is not a strong acid due to its electronegativity. And by definition, perchloric acid is also a strong acid. And going back to the concept of corrosive, okay? This has a strong, very strong oxidation power, and it can also be a very good dehydration agent, okay? So when we mix sugar with sulfuric acid, well, we get carbon, right? Because it basically oxidizes the sugar back to carbon. That makes sense? All right, so I think we touched most of the properties. I know you guys already learned that. Okay, so you get this smooth or slimy feeling for these basic compounds, and that is in textbook. I honestly don't know why they feel slimy, but for example, when you have some limestone powder, which is CaCO3, right? Once it gets wet, we will get certain amount of hydroxide, right? And they are slimy. All right, so let's talk about strong base. So generally, the hydroxide of these guys are strong base. Okay, and also their carbonate will be strong base as well. The most common example would be sodium and potassium carbonate. They're commonly used in organic synthesis. Okay, base generally have, so M stands for metal. Okay, the metal cation. Depending on the charge, it can be in the oxide form. It can be in hydroxide form, and depending on the charge, you might be able to get MO and OH2, okay? So such as calcium hydroxide. But again, calcium hydroxide is a strange case because it has limited solubility. We'll come back to that later on, okay? Generally, we focus on the first column, okay? All right, so for pH, everybody mentioned pH. So how is pH calculated? When you see the P, it generates a negative log of concentration of hydronium. So this is an improper way to write it. The concentration of the hydronium ion. So you do a negative log. If you want to figure out this, you just do simple math, okay? Everybody gets this? Okay. When we talk about pH, we have scale 1 to 14, right? So by definition, the equilibrium constant of water we set that to pH is 7, okay? But a lot of time, if you actually take a pH meter, discuss with your partner why the pH is not 7 for a lot of water that we have around us. So first we will talk about why it could be acidic and why it could be basic. In what scenario it could be acidic, a natural water that you will have. In what scenario it will be acidic and why. Think about a scenario where we have CO2 in air, right? And then when it dissolves in water, it forms carbonic acid. So partially, you have hydronium, right? You have these hydronium ion, and this is one way to make water acidic. It's also possible that your water being exposed to some acidic substance, okay? You have very small, this is not a triply distilled, deionized water, okay? You have these ions in the system, and some of these ions resulted from the weak acid that is being added to the water, then that make it slightly acidic, okay? So it's very common. I mean, a lot of time you assume water will be 7, but a lot of time when you measure the pH, it would be like 6.5, okay, 6. Okay, in what case the water will be basic? The perfect example, if you go to 7-Eleven, they have these water that branded themselves as basic water. So usually these are mineral water. I mean, of course, a lot of time it's a marketing. They say this is better for your health, but mineral water, because you have all these metal ions, they have these very complex equilibrium with the water molecules. So it will change the amount of hydroxide in the system. So you have to recognize water is a very strange molecule that itself, of course, with the help of other additives, itself can pick up a hydrogen or lose the hydrogen to another water molecules. Okay, so for a perfectly neutral, so 7, the concentration of hydronium and hydroxide are equal to each other. And given that constant, because we wanted to put into a relative scale, 1 through 14, the concentration at pH 7 would be neutral. So have anybody heard about Lewis acid and Lewis base? So the third definition, which we will talk about next period, is Lewis acid and Lewis base. You have to remember the difference between Arrhenius definition and Bronsted-Lowry definition, okay? So this, Arrhenius said, acid are substances that release H+, and base are the one that release OH-. Bronsted-Lowry's definition is it donates or accepts protons, okay? So for acid, it donates proton to water. For base, it accepts proton from water. That makes sense? Accept proton, okay? And when we talk about Lewis definition, it's talk about electron pair, and we'll talk more about it next period. And now, for those of you who are new to this class, For last semester, when Professor Craney did experiment, he simply asked you guys to fill out these sheets every time he did an experiment. So this is a checklist or a roadmap that helps you to become a scientist. So as a chemist myself, usually when you do reaction, you have to observe what happened, right? During the course of reaction, okay? You observe, and you usually will form some sort of hypothesis, okay? And to explain what you observe. For example, your reaction is going too slow. Is it because you didn't add heat, or is it because the temperature too high? Then you will come up with some potential tests that you can test for your hypothesis. But before you do the test, you should probably already have a plan in mind. When you do the test, it gives you a positive result or it gives you a negative result. So before you even do the test, you should even have a backup plan for your outcome of your experiment. Okay, that makes sense? Because I know a lot of you already learned this chemistry before, but more importantly is you practice your English skill. By doing these writing assignment, it's going to improve your grammar and improve your logics. So I have something labeled solution A and solution B, okay? And I'm going to tell you what's in there, okay? So in flask A, I have potassium iodide, okay? So it's dissolved in water, okay? So you don't have to guess what the solvent is. You have sodium acetate and a type of reducing agent. I don't want to confuse you guys. It's a reducing agent. It has a reducing power. Solution B would be an oxidant, which is hydrogen peroxide of certain concentration, and acetic acid, and water, of course. So these two aqueous solutions. So I will do a simple demo first, and then I will have you guys discuss what the next experiment you want to do, and I'll let a volunteer or two to actually do the reaction, okay? So also I want you guys to notice is the time that takes for the color change to occur. So first, I'll mix them at 1-to-1 ratio. Hopefully it works. So since they will react with each other, so I don't want to contaminate them. So about another 300 ml. Okay, so it's quite fast, okay? I mean, this is different than what I did before when I was in the lab, all right? So I didn't expect this. It's supposed to take a few seconds, but you did see a color change. So this is 1-to-1 mixture, and now observe what happened. You can come up if you want and write it down, okay? And then potentially explain what happened, okay? Okay, now there are some solids are present at the air-water interface. Okay, so you can also write about this observation and explain why it's happened at the air-water interface. Okay, so the second experiment I would do is I'm going to take a spatula and I'm going to feel. So this is just tap water, okay? One beaker is tap water. I'm going to put it on over here, all right? In a different container, I'm going to put alcohol. This is ethanol, 95% ethanol. Okay. So I'm going to sample a little bit of these solid out. Okay, I'm going to put it in, this is tap water, okay? All right. So then I'm going to sample a little bit solid out. You better stay away. Okay. And this is ethanol, okay? Okay, so this is a second clue that you're gonna get, okay? This solid is soluble in ethanol. Why? Okay, it's not soluble in water. But how come some are sink and some floated on top of water? Okay, so now go write down your observation and write down your hypothesis. Okay, and then these are your clue here, okay? And then this is what this reaction will look like after it being an hour or two, okay? This is what I did previously, and you can come observe the difference between these two reaction mixture. So this is after a while, noticing the color difference, okay? So initially, the first experiment that we did, it's 1-to-1, about 300 ml each of solution A and B, okay? Experiment 2 is solid solubility test. In water, not soluble. In ethanol, it is soluble. All right. So anyone want to think of other experiment to do? You guys still have like 15 minutes. Okay. Then we'll do another experiment. I'm gonna take this sample and adding solution A and see what happens. So this is the water solubility test. We can see the solid that formed is not soluble in water. So going back to efficient mixing, it's already stirring pretty fast, right? Now you can tell when you stir a reaction, they don't always mix very well. You see that? Okay, now the color stuff all gone. Okay, now it's perfectly clear, right? Just look like the starting solution. Okay, so now we have 2 volunteers. So anybody want to ask them what they want to do? I don't know if they know what they're doing, but you guys can help your classmate out, okay? What's the best reaction that you guys think should be done next? 随便啊。你就直接拿个，或者3:1呀。但是量不要加那么多，你可以用 graduate cylinder， 你可以用那个2桶 ，OK？ 因为我另外一个 solution 没有那么多。然后用完 A 之后，你冲一下再用，好不好？然后用有手套的手去拿那些东西 ，OK？You can, yeah， 你可以拿下来。你可以做小量的或者做大量的都可以，然后磁石在这边。那就弄小量。你倒的时候，你另外一个手没戴手套，所以你你不要倒到同学哦。这很少啊。 So you should write down what, because they can't read the graduate cylinder, you should write down how much you add. So experiment 4. How much A? So is that A? Okay. How much A did you add in? 那这个冲一下再用。对对对。Okay, so before you do anything, you should let them know you're about to add them together, right? Okay, so now noticing, I mean, the reason why I do this reaction is it has to do with reaction rate, and it's associated with so many different concepts we already mentioned. All right, so now you can see the rate of the solid forming is much slower than before, right? And there's no precipitate that form at the interface yet.